Okay, next up on our list is the heat equation, which involves a first order derivative with respect to time and a second order derivative with respect to space. The space-time domain we have is defined by a one-dimensional physical domain, which is marked by positions x that range from 0 to L and all positive times. And since we have those first and second order derivatives, we need to have two boundary conditions that define our field variable. So we have g1 of t that is prescribing the value of our field variable at x equals 0. As well, we have g2 of t that prescribes the same the value of the field variable at x equals L. We also need an initial condition because there's a first order time derivative in the governing equation, and in this particular case, the value of the field variable at time equals 0 is completely defined on all the points in our spatial domain by a function labeled as u sub 0 of x. Visually, we can look at what we have prescribed and what our governing equation is on the space-time continuum. So the yellow straight line below defines our domain, which ranges from 0 to L, and the initial condition of the field variable is completely described or prescribed by this function u sub 0 of x at time equals to 0, and on the left and right ends of our domain, g1 of t and g2 of t define the value of u at all times, and the governing equation is valid on the interior of the space-time continuum. There are two basic approaches for developing numerical solutions to this problem. One is the so-called semi-discretization approach. The other one is the full discretization approach. In the semi-discretization approach, as the name implies, we discretize one of the variables, free variables we have. So, for example, we can discretize the spatial variable and leave the temporal derivative analytic. And if we do that, then we're going to end up with a system of ordinary differential equations in time. And the solution of that is something we have already learned in the previous chapter. We can use any ODE solver. In the full discretization, again, as the name implies, both the spatial and temporal variables are discretized, which gives you a system of linear equations, whether you discretize the derivatives with an implicit or an explicit formula. And then you can solve those system of linear equations to determine your field variable at all times and positions using a solver, direct solver like a Gaussian solver or an LU solver, which we have also learned previously. Visually, this is what we have in the space-time continuum. In the semi-discretization approach, which is what we're going to discuss first, the x direction the x variable is discretized with spacing h sub x. Such that each position, discrete position along the x direction is denoted by x sub I, which is given by I minus 1, that index that was the subscript, times hx. So the discrete variable is x and the continuous variable is time, t. Since we have discretized along the x direction, then we need to approximate the derivative we have along the x direction in our governing equation. And since this is a second order derivative, let us use the central difference formula, which is second order accurate. And this approximation is going to be applied at all the interior points we have. Note that this I index does not include 1 or an x plus 1 because at those locations the field variable is already completely prescribed and known through the functions g1 of t and g2 of t. So let us also, before we make any further progress, create a shorthand notation for our partial derivative with respect to time, evaluated at x sub I and t as u dot sub I of t. So t is still a continuous variable, it's not discrete, and only discrete variable is the x variable. That's why we have only single index. Likewise, if we look at the actual field variable itself, evaluated at x sub I, comma t, we will denote it as u sub I of t. And the same is true for the driving function f. Once we substitute the second order derivative central difference formula into our governing equation and rearrange it a little bit, we're going to arrive at the equation, semi-discrete equations we see in the blue box here. So we have the field variable fully discrete along the x direction, but fully continuous along the t direction, given to us, or having to obey this equation in the blue box. And we also have our boundary conditions and initial conditions. So let us reproduce those equations in one by one, all the equations we have. And if we write them down one by one and arrange them in a matrix vector format, we're going to see the following. We're going to see the continuous time derivative of the field variable at all interior points on the left-hand side. So we have u sub 2 of u dot sub 2, u dot sub 3, all the way to u dot sub n sub x. And on the right-hand side, we have a constant coefficient matrix multiplying our field variables at all the interior points at all times. For example, starting with u sub 2 of t and ending at u sub nx of t. And the last term, the last vector on that equation, semi-discrete equation, is going to be the terms that emanate from the driving function, f, as well the prescribed boundary conditions on the left and right hand sides. So we can write the equation that we have seen more compactly. If we do that, what we're looking at on the left hand side is a vector of u dots and a matrix A multiplying a vector of u's, and that is being added on by a vector of f, which comprises both the driving function, if we have any, as well as the boundary condition functions g1 and g2. We obviously need to have a first order boundary condition, initial condition for our first order system of ODEs, and that is also given to us by the prescribed function u sub 0, which tells us the values of the field variable at all positions at time equals 0, which can be written more compactly as the vector of u's at time equals 0 is equal to a vector which is prescribed u sub 0. With the two combined, what we have is a system of ODEs, first order and linear in this case, with a proper initial condition. We should be able to solve this using any ODE solver. For example, we can use the linear ODE solver Euler-Cis that we have learned previously in our discussion of ordinary differential equations. There's a slight typo in that f vector. Please look at your notes and correct the typo. There's a missing plus sign, and the g term, I think, should appear in the first position in that vector. Now let's talk about the explicit full discretization. In the explicit full discretization, both variables x and t are discretized. So we have the spatial discretization already in hand. Now we're going to do the same thing and do a discretization of the t-axis. Let us choose nt points along the t direction and define the discrete time instances t sub k through this index formula, which says t sub k is equal to k minus 1 times ht, ht being the time increment between our time slices. So when we look at our problem graphically, what we have is the space-time continuum discretized along both directions, and our goal is to basically fill in the values of u in the red diamonds, except for the left side and the right side, where we have the boundary values prescribed, as well the first time slice where we have the initial condition prescribed. Since we have discretization along both directions, we can create the shorthand notation for our discretely sampled field variable. If we sample it at x sub I location and t sub k time, we can simply call it as u sub I superscript k. We can do the same thing to our driving function f. So we're talking about an explicit full discretization here, which means I'm going to adopt a forward Euler formula for my time derivative. We already had the central difference formula for our spatial derivative here, and now we are appending it with the first order derivative formula, which is first order accurate. And if we plug those equations, these approximations into our governing equation, what we're now looking at is a fully discrete scheme. And obviously we're seeing two indices, I and K, I denoting positions along the x direction and K denoting positions along the time direction. We have our boundary conditions and initial conditions as before. And all the equations we have are reproduced here for your convenience. And before we move on further, let us just create a shorthand name for this ratio, gamma, which is A times, A being the characteristic value that we had in our governing equation, times the spacings that we have chosen along the time and the space directions. If we introduce that name into the equation that we have in the blue box, we can rearrange it as follows. And there's a slight typo in here where the arrow is pointing, there's a missing plus sign, so please correct that. Let us reproduce that equation here. It still has the typo. And let us see how we are going to go about solving this system of equations and impose the boundary and initial conditions. So what we have here, first of all, are the boundary conditions, which are prescribed on the left and the right hand side of our domain for all times through the functions g1 and g2 of t. So we know the field variable at those locations at all times. We don't need to solve for them. Likewise, we have our initial condition telling us the value of our field variable at time equals 0. So we don't need to solve for the value of our field variable there either. And our goal then is to determine the value of our field variable at all those interior points in those red diamond areas. And if we take a closer look at the equation we have, say, if we look at u sub I superscript k plus 1, meaning at time tk plus 1, so my actually circle appeared in the wrong place, but just at some time, if we look at our solution and look at the left-hand side of our governing equation, what we see here is that its computation is going to require values from the previous time slice, k. So it's going to require the value of the field variable at the previous time slice to the left of it, the central position at the previous time slice, and at the previous time slice to the right of it. Along with the value of the driving function, we should be able to calculate the value of our field variable inside the red circle. So this means that only data is needed from the previous time step, and this is no surprise. We were going after an explicit full discretization, and this is what we have. It's an explicit method. So its solution is going to be pretty simple. We are not going to have to solve a system of equations and such. However, we're going to pay the price in terms of stability, and this method is only conditionally stable. If you actually carry out a rigorous stability analysis, you'll see that the ratio that we have defined before, gamma, has to be less than a half in order for our numerical method to be stable. In other words, there's some constraint that forces us to choose the time and spatial increments carefully, and the ratios, when plugged in here, will have to satisfy this constraint. If we do so, then our solution is going to be bounded, and in particular the error that we have committed, maximum error that we have committed in a given time slice, is going to be the upper bound for the maximum maximum error that we're going to get in the next time slice. And as well, if you notice, if we wanted to do, for example, refinements, then we have to do it carefully. For example, if you wanted to get a more accurate solution by refining our increments along the spatial domain, and say by dividing our spatial increment by half, in order to keep the solution method stable so that we keep the gamma ratio constant, we need to divide the time increment by 4 so that this gamma ratio is kept constant. So just blind refinement along one direction may actually destroy the stability of your solution. So you have to watch out for that. As a final note, without really actually carrying out the rigorous analysis, we can just say that the maximum difference between the analytical solution, if we had access to it, and the numerical approximation that we have sampled at all positions and times that we have discretized, is of order ht plus hx squared. So it's first order accurate in time and second order accurate in space. And in a given scenario, it's going to be a combination of these factors that tells us how much error is going to reduce when we, for example, refine along the time and the spatial directions. Let's take a look at the MATLAB implementation quickly, and I urge you to read this more carefully yourselves. And this is the heat equation solved with explicit full discretization. So this is the second option that we have described, not the first semi-discrete option. This is the MATLAB code for, again, explicit full discretization. So what we have here is the function handle, and on the right-hand side we have our coefficient for the A for the governing equation, our right-hand side driving function f, our initial value function, our boundary conditions functions g1 and g2, and some other variables such as the length of our domain, the maximum time value capital T of our interest, and the spacing that the user wants to use along the x and t directions. After initializing some parameters, we can move on to generate the grid points and fill in our field variable values with the given initial and boundary value functions, g1, g2, and g1, g2, and u sub 0, and then go on about evaluating, just filling in the interior values by moving at one time slice at a time. So when we fill in the value at k equals k plus 1, then we'll be able to, once we've done the determination of the field variable at all those times, we're going to be able to move on to the next time increment. So we have a loop over the time increment that ranges from k equals 1 to nt. And this is quite simple. Let's just apply this numerical technique to a problem for which we have actually the analytical solution. So here in this case a is equal to 1, so u sub t is equal to u sub xx. Let's say that the size of our domain ranges from 0 to 1, and we're interested in figuring out our solution at all positive times. We have a given initial condition that says the value of the field variable at time equals 0 is equal to sine pi of x, and then we have both on the left and right hand sides of our spatial domain at x equals 0 and L, our field variable prescribed to be 0 at all times. So that's a pretty simple boundary condition. If we evaluate the analytical solution for this problem, if we solve it, we end up with this function. You can check to see whether this actually satisfies the governing equation, and it does. And we can certainly see from a plot of it that it actually satisfies our initial condition, which is like a half sine, right, at time equals 0. As well, it has values prescribed to be 0 on the left and the right hand sides, and it changes on the inside according to the governing equation we have. So let's see how our numerical technique will fare in trying to approximate the solution with a first central difference approximation for the second derivative and a forward Euler forward difference approximation for the temporal derivative. If we look at the parameters of our problem, we see that our A was equal to 1, which I mentioned before. The length of our domain is 1, and our maximum time of interest is 0.2. So when we look at the values of hx and ht and look at that ratio of gamma we have described before, we can equivalently write it as, now for this problem, 0.2 times nx squared over nt. And if we are seeking a stable solution with our explicit full discretization scheme, this ratio with the chosen nx and nt values must always be less than half. Otherwise, the solution will blow up. So let us just solve the problem with these sequences of nts and nx's. Let's just pick the nx to be 3, nt to be 6 first, and then try the solution again by having nx equals 6 and nt equals to 24. And it's no surprise I'm doing this. Why? Because if I have double the size of points I have along the x direction by increasing them from 3 to 6, I need to quadruple the number of points I have along the time direction to keep the same gamma ratio, which is going to be achieved if I pick the next nt to be 24. And we go on like that for nx equals 12 and nt equals 96. For all these discretizations, I am achieving a value of gamma of 0.3, which is less than 0.5. So I should be stable in all these calculations. Let's just plot the solution for one of those, for example, the most refined version of our solution. where we have chosen nx to be 12 and nt to be 96. On the left-hand side in the three-dimensional plot, you see the field variable computed. The left and right-hand sides and the initial time are prescribed, obviously, and all the interior points are computed using our explicit full discretization scheme. It looks very much like the analytical solution we have plotted in the previous slide. And if you actually subtract the two and plot their difference as the error, you see that the error is really small. It looks as if the error is less than, at any location, 1.5 times 10 to the minus 3. Compare that to the maximum value of the solution that you have recorded to the left. On the left plot, you see that this is a very, very small error indeed. If we actually look at the errors that we have encountered, the maximum errors that we have encountered for all the three different successively refined discretizations, we see that the error at first is 1.8 times 10 to the minus 2 maximum error, and it goes on from there. And the ratios of these errors are approximately, I think, 4. So since we have obeyed that rule of keeping the ratio of our gamma constant, then the error here was obviously dominated by the second order accuracy of our spatial discretization. So when we have doubled the number of points that we have along the x direction, the error was reduced by a factor of 4. So this was pretty good. Now let's just attempt the same solution with a different discretization. This looks quite refined. I mean, certainly we have more than 9 points along the x direction. We have 20. But if we pick the temporal discretization willy-nilly and just pick it 20, it looks like refined enough. We see that the gamma actually in this case is 4, which is much, much larger than our critical value, half. So if we attempt a solution like this, it will be unstable. And if you actually do that, plug these parameters into the MATLAB routine that we have looked at before, you'll see that the solution blows up really quickly. And the reason the solution looks so weird on the left plot is that because there are some really extremely large values of the numerical solution, which makes all the other values look so small and flat. But certainly, if you just plot the error is immense. So this solution is garbage. The solution blew up because the number of points along the x and t directions we have chosen did not satisfy our stability criteria. We can also take a look at the heat equation with implicit full discretization. All we have to do then is just change the temporal derivative from being a forward Euler derivative to a backward Euler derivative. We had above the central difference formula for the spatial derivative. So now if we plug these into our governing equations, what we have is again some fully discrete formula, except this time it's actually implicit because we are using the backward Euler formula for the temporal derivative. We have our boundary conditions and initial conditions as before. So the governing equations that we have are reproduced in here. And after defining again that gamma coefficient, where I don't have the typo anymore, I have the plus sign intact in its place, we have the equations shown. Negative gamma multiplying u superscript k subscript I minus 1, etc., is equal to etc., etc. So in this equation, the values of the field variable at time equals tk are arranged or lumped onto the left-hand side, and the value of the field variable at the previous time is left on the right-hand side. The driving function is always known anyway, so we're not really concerned about that. So if we look at these equations and evaluate them at all the interior points we have, we're going to see that what we have is a system of linear equations, and our coefficient matrix is a tridiagonal system, and all we have to do is just solve for the u's at all the interior points we have at all times, at any given time. And so once we have done this, starting from an initial condition where we are being given the value of the u, the field variable at time equals 0, we can certainly march on in time. And every time we want to do this march, we have to solve the system of equations to be able to get the value of u sub k, u superscript k, from the values of the u superscript k minus 1, which appear on the right-hand side, as well as the driving function and the boundary value functions we have. So this is not a system of ODEs. This is a fully discrete linear algebraic system, but it's a linear system, and we can use Gaussian elimination, LE decomposition, whatever you want to have. The most obviously suitable solver for this particular case is the tridiagonal solver, which specializes for a banded system, and in particular a tridiagonal system, which we have talked about in the previous chapter, one of the previous chapters. The disadvantage here is obviously we need to solve a system of equations, so it's much more expensive than the fully discrete explicit version. However, the method can be shown to be unconditionally stable, so there are no constraints on space or time increments. The more you refine, the more accurate solutions you get. You don't have to pay attention to the ratio of the points along the x and t directions to try to satisfy stability criteria. Nevertheless, the accuracy of the method is no different than the the forward Euler method, which was the explicit one. It's still first order accurate in time and second order accurate in space. So nothing has changed as from that. MATLAB implementation, I urge you to take a quick look at it on your own. But again, we have our inputs, which consist of the driving function, our initial and boundary value functions, the size of our domain along the x and t directions, as well the number of points that the user wants to use along x and t directions. So heat 2 will return the value of u computed through the implicit full discretization scheme. Initializations are made, and then the function is filled with the initial value at time equals to 0, and also it's filled in with the values of the boundary values on the left and right hand side by g1 and g2, and some vectors are constructed which form the diagonal, upper diagonal, and above the diagonal and below the diagonal terms of the constant matrix for the time, and then we solve it with a tridiagonal solver. And once we have the value for one time slice, we can just keep repeating this procedure and move time slices and get values of u at all the interior points. We can look at the same problem to see how well our algorithm, fully discrete implicit algorithm, fares. This is the case which was the unstable case for the explicit full discretization. Now you can see that it is actually fairly accurate and definitely stable. The error is very, very small. It did not blow up, even though the ratio gamma is different than a half. We don't have such a constraint in the implicit full discretization, so we ended up with a really good solution.